Hey physics students, this is the calculation part of Lab 4, projectile motion. Okay, so let's see what we got to do. We go to course content, of course, and click on lab. You've all done this a few times now. I go down here to Lab 4, I click on Lab 4, and here's the document that's attached to it, so I'm going to open that. Or I could save it. I'm just going to open it. You would probably save it on your desktop. Then I'm going to bring it over here so we can see it. And I'll click on Edit Document. Okay, here's a little schematic diagram. Here's H that you measured, the height from the floor. Here's capital R, the range. That was measured from the edge of the table horizontally. And here's the ramp, and there's the distance D. This right here would be the angle theta, the tilt of the tilt of your ramp. Okay, so there's the equipment we used. So here's the measurement portion, the procedure. I used 80 centimeters for distance D because that was already marked on my launcher. You don't have to use the same ramp. So you can make your own, make any kind of ramp you want. You can even use a piece of cardboard, I guess. I don't know how sturdy it would be. A board is better. All right, so you write in your values for the distance along the ramp you're using, what angle you're using. The angle should be between 10 and 20 degrees somewhere. Then measure the distance, launch a projectile 3 times, locate the point of the floor. This is a range. So we're going to have 3 measurements of this and take the average. And then you're going to paste a picture of your apparatus here, of course, as usual. Now, we're going to begin the calculation part. The first thing we're going to do is calculate the acceleration of the rolling ball on the ramp. This formula is not in your book. Galileo didn't know it either. The formula they have in the book for the acceleration along the ramp is just g sine theta. This 5/7 isn't there. That's for a sliding object. So this is for a rolling object. So it's not in your book, but I know it. So you just take 5/7. So we're going to calculate the acceleration of the ball as it goes down the ramp. We take 5/7 times 9.8 times the sine of your angle. So report that there. So I would write that A equals So I'd put my acceleration in there for that part of the calculation and make it blue. I don't know what mine comes out to be. Now I want to calculate the speed as after it gets off the ramp and starts rolling across the table. When it's rolling across the table horizontally, it's moving at a constant speed. So that's going to be the speed that it leaves the table horizontally. So I'm going to use this equation. The initial velocity when I started down the ramp was 0, so this is 0. This is 2. This is the acceleration I got above, and this is the distance along the ramp that it went. In my case, 0.8 meters. So I would report that, and then I got to take the square root of that, obviously. So I would report the velocity here, put that in, and I'd put in, and put all these quantities have to have units, obviously. This would be meters per second. This would be meters per second squared up here. So I need to get that in there in blue. I would show my work, say what numbers I did here. I would put the square root of 2 times A times D, put it in blue. Now, when it leaves the table horizontally, it's it's falling in the vertical direction while it's moving horizontally at a constant speed, the same speed it left the table with horizontally. So the initial velocity in the y direction when it leaves the table, this is from chapter 3 here, the initial velocity when it leaves the table in the y direction is 0. And the initial y direction is, the initial y position is 0. And when it hits the ground, this would be minus h. The y coordinate would be minus h. And so that's equal to minus 1/2. G is always the number 9.8. The little g symbol never has a negative sign associated with it. The negative sign is right here. So I would put in minus h over here. I'd put 0 in for this, 0 in for this, and I would calculate t. This is the amount of time it takes to fall once it leaves the edge of the table. And so I would calculate t. I'd show my work, and I would get t equals whatever you get. And I'd put it in blue. Okay, now the range, this is the x direction for projectile motion. The initial x position is 0. This is the velocity that it left. The initial velocity in the x direction is the same as the velocity in the x direction throughout its motion, and this is t. So I would calculate r from this. That's going to be the x horizontal distance the ball goes. That'd be the horizontal distance the ball goes before it hits the ground. Put it in blue. I'd show my work how I did that. Okay, finally, how do the measured distance and calculated distances compare? The way we compare things is with a percent difference formula. So I would, in my conclusion, I would calculate the percent difference between the calculated and measured values of r. So I would take the difference between the two. I would take the calculated. I'd take the biggest minus the smallest, because this is an absolute value. Percent difference is always positive. I would take the calculated minus the measured, and I would divide that by, the calculated. That's usually the way we do it. And then I'd multiply that times 100%. This kind of tells you, this number tells you like whether you're in the ballpark or not, whether you've made any glaring errors. You know, anything less than 10% difference for experiments that are being done in your basement, I'm very impressed by. If you get less than a 10% difference, you should feel quite proud of yourself, because it means you did the procedure pretty carefully. And then, do you think that, do the kinematic equations that we have been using seem to work in practice? Well, if you get less than 10%, that's working. If not, why not? Why do you think? What would you think is the biggest source of the your disagreement if you get a massive disagreement? You want to try to eliminate any mathematical errors, of course, or measurement errors, or unit conversion errors, or things like that. We don't really consider those acceptable errors in a lab procedure. Errors due to your house not being level. I had to level my. I had to get a different table because my the table I used last time was just had a lip on it, and it just didn't work out, so I had to get a different table, as you can see. I found the table I used in the alley, by the way. Anyway, so don't get too stressed out about this conclusion, and don't make it too long. Too long is worse than too short. A couple sentences. You don't have to spend a lot of time on that. Okay, then what? Then I save. I save it on my computer in case I want to go back and make any changes to this. And then I convert it to PDF. On this, export as PDF. Export. And then I go back to Blackboard, of course, my page where the lab is, and then I browse my computer, and I don't know where it saved it. I wasn't paying attention. Maybe on the desktop. I wasn't paying attention when I exported it to PDF. There it is right there, Projectile Motion PDF. And then don't forget to click Submit at the end. You can't see it because my face is over the Submit button. So click Submit on the lower right, and you're done with lab this week.